Within the vastness of the universe, there exists something quiet, easily overlooked yet profoundly decisive. We are used to thinking that what matters most is what stands out, what shines, what moves, what demands attention. But often, it is the opposite. It is the silent, expansive spaces that shape how we perceive scale and distance in our own lives. A long stretch of road between cities, an open ocean with no land in sight, a silent room after everyone has left. These spaces are not truly empty, but compared to what surrounds them, they feel vast, unsettling, and strangely powerful. They influence how we move, how we measure distance, and how large the world feels around us. Very often, it is the space between things that defines the size of the world. When we turn our gaze toward the universe, we instinctively focus on what shines: stars, galaxies, and clusters of matter bound together by gravity. Yet on the largest scales, the cosmos follows the same pattern we recognize from everyday life. Most of the universe is not made of objects, but of the immense spaces between them. Astronomers call these regions cosmic voids. At first, voids appear to be nothing more than gaps, places where nothing important is happening. But this impression is deeply misleading. The universe is expanding, and its expansion reveals itself most clearly, not where matter is dense, but where it is scarce. In these vast cosmic voids, gravity loosens its grip, space stretches more freely, and the large-scale structure of the universe is slowly reshaped. Stay a little longer, because once we understand how emptiness behaves on cosmic scales, we are forced to rethink what expansion truly means and whether the universe ever needed to expand into anything at all. So, if expansion is not an explosion into a waiting emptiness, but a change in the fabric itself, the natural question is, which parts of that fabric are actually doing most of the changing? To see that, we have to look past the places that draw our eyes and pay attention to the regions that almost disappear from our maps. When people are asked about the largest things in the universe, they usually reach for something solid. A star more massive than our sun, a galaxy with its swirling disk, a cluster of galaxies bound together by gravity. Some might imagine chains of clusters, the so-called superclusters, forming grand cities of matter on the largest scales we can picture. It feels natural to assume that greatness in the universe belongs to what is full, but the universe quietly refuses that intuition. When astronomers mapped galaxies in 3 dimensions, they did not find matter spread smoothly, like dust evenly mixed in air. They found strands, knots, and sheets of galaxies, separated by enormous regions where almost nothing shines. Those regions, the cosmic voids, do not shout. Yet by sheer volume, they occupy most of the universe's space. Think of the familiar hierarchy. A galaxy like our own holds hundreds of billions of stars, orbiting in a disk perhaps 100,000 light-years across. A cluster can bind together hundreds or thousands of such galaxies, filling a region a few million light-years wide. Beyond that, superclusters and filaments stretch for distances so large that language starts to blur. We stack object upon object, always adding more matter, and assume that by piling up enough substance, we will reach the universe's true giants. Yet if you step back far enough, those giants become thin. The clusters and filaments that seem so massive turn into bright threads and nodes in a nearly transparent medium. By volume, the luminous web of galaxies occupies only a small fraction of space. The rest is made of regions where the average matter density is far below the cosmic mean, often less than about 1/10 of it. These are not little gaps you can ignore. They are the main environment, If the universe were a city, the galaxies would be the street lamps, and the voids would be everything else. In human life, we often misjudge scale in a similar way. We remember crowded rooms, intense days, the moments when everything felt full. But if you look carefully, most of a life is made of intervals. Waiting, crossing, pauses between decisions. The few events we cling to as what really happened sit like small clusters inside long stretches of ordinary time. The structure of a life is defined as much by those quiet expanses as by any single moment that fills them. Cosmic voids play a similar role. They are not simply empty gaps between the real structures. They help define where those structures can exist at all. In simulations and surveys, voids appear as underdense regions that slowly push matter outward, toward their boundaries. As the void expands relative to its surroundings, matter is evacuated from its interior, piling up in thin walls and filaments around it. The galaxies you see in a deep image are often perched on the edges of vast invisible basins. This is an odd kind of dominance. Voids do not win by gathering things. They win by occupying space. Their influence is not the tight grip of gravity pulling everything inward, but the gentle insistence of almost nothing pushing things away as space itself stretches. In a sense, the universe's architecture is drawn from two competing tendencies: matter trying to clump, and emptiness quietly expanding. On large scales, the second tendency takes the lead. It is important to be precise about what this almost nothing is. A cosmic void is not a perfectly bare region with absolutely no particles, no fields, no radiation. It is a region where the density of galaxies and of the dark matter that scaffolds them is much lower than average. Astronomers quantify this using an underdensity parameter, how much the local density falls below the cosmic mean. Voids are typically places where that underdensity is strong, where the number of galaxies per unit volume can be an order of magnitude lower than in the surrounding web. If that sounds abstract, translate it into distance. In a rich cluster, you might not have to travel very far before passing from one galaxy to the next. In the interior of a large void, you could in principle travel for tens or hundreds of millions of light years before encountering a galaxy bright enough to be seen with our telescopes. The emptiness is not absolute, but from the perspective of creatures who live inside a galaxy, it may as well be an ocean with islands so rare that the horizon almost never shows land. We are not placed at the center of such an ocean. Our own galaxy sits in a filament, on the edge of nearby voids, part of a fragile web that outlines the boundaries of emptier regions. When we look out, we see other filaments and clusters, and subconsciously we treat those bright structures as representative of the universe as a whole. It is like living in one of the few dense neighborhoods in an enormous country and assuming the whole landscape must be built that way. There is a more personal version of that illusion. Each of us lives at the intersection of relationships, conversations, responsibilities. Our days are dense with people and objects close enough to touch. It is easy to forget how quickly that density falls away. A modest journey by plane takes you over vast stretches of uninhabited land or sea. A small change in life circumstances can turn a crowded social circle into a thin ring of occasional contacts. We are local concentrations of experience in a space that, on larger scales, is far more empty than it appears from inside our own cluster of concerns. Cosmic voids force cosmology to confront this imbalance directly. When early maps of galaxy positions revealed enormous holes in the distribution, many astronomers suspected mistakes, incomplete surveys, selection effects, artifacts created by the way data were collected. Only when independent surveys, using different instruments and methods, kept finding the same great empty regions did it become clear that the holes were not errors in the picture. They were part of the picture. Once you accept that, another shift follows. You can no longer think of the universe as a mostly filled container with a scattering of incidental gaps. Instead, you begin to see a mostly empty environment in which matter has managed, here and there, to draw thin lines and knots. In that framing, the presence of galaxies looks less like the default and more like a rare outcome of initial conditions and gravitational evolution. The background state is not fullness. It is scarcity. This has a quiet existential edge. If the universe is dominated by regions where almost nothing ever happens, at least in the sense we usually care about, then our familiar world is not a typical sample. We live in an overdense exception, a narrow band where matter, complexity, and eventually awareness have found a foothold. That does not make us central. It makes us contingent. The very fact that we can look out and name voids is a side effect of living on the rind of one. And yet, the dominance of absence is not only a philosophical discomfort. It has dynamical consequences. Regions that are underdense expand more rapidly than the average, while overdense regions lag behind as gravity tugs them inward. That means the universe's growth is not uniform in its details. Space stretches a little more freely in the places where there is less to hold it back. The largest things in the universe, the vast zones of relative nothingness, are also the places where the story of expansion is written in the clearest lines. So when we ask what role voids play in the universe, we are not asking about side characters. We are asking how the dominant environment, the sea in which the cosmic web floats, participates in the ongoing change of scale itself. If most of space belongs to almost nothing, then the meaning of expansion cannot be understood without listening closely to how that almost nothing behaves. But before we can listen to how emptiness behaves, we have to understand what we mean when we say that the universe itself is growing. The word sounds simple, almost domestic, but it hides a change in space that has no easy comparison in our ordinary lives. When we hear that distant galaxies are moving away from us, our first picture is almost always wrong. We imagine hard little islands of stars flying through a pre-existing void, like sparks thrown off from some ancient explosion. We place ourselves in the middle, or somewhere close to it, and see everything rushing outward from a point. It is an instinctive scene. Things leave. We stay. The observations that led to this picture were straightforward in one sense. Astronomers saw that the light from distant galaxies was stretched toward longer, redder wavelengths. The farther a galaxy was, the more its light was shifted. Light carries, frozen into its waves, the imprint of motion. When a source moves away, its waves are stretched. When everything far away shows that same stretching, and the amount of stretching grows with distance, it is natural to say, the farther they are, the faster they recede. But those words, faster and recede, smuggle in more than they explain. We are used to speed being a measure of how quickly an object moves through space. A car has a position, then a slightly different one, and the difference divided by the time between them is its speed. We imagine galaxies in the same way. At one time they are here, at a later time they are farther away, and so we imagine them pushing through a fixed, neutral background. General relativity suggests a quieter, stranger picture. In that framework, space is not a stage. It is part of the cast. Distances between things are not carved into an external grid. They are properties of the same fabric that also carries gravity. When we say that the universe expands, we are not describing galaxies accelerating through a static void. We are describing a change in the distances between points that are, in a sense, staying put. A familiar analogy is a rising loaf of bread with raisins scattered throughout the dough. The raisins stand in for galaxies. The dough stands in for space itself. As the dough rises, each raisin sees all the others moving away. The more distant raisins recede more quickly, because there is more dough in between to stretch. None of the raisins has to crawl or swim through the dough for this to happen. They can remain at rest relative to their local bit of dough and still find that every other raisin is farther away than before. Even this picture is limited. It risks turning space into a substance, something like a medium that can swell or shrink on its own. But it is useful for unhooking one particular mistake. The receding of galaxies in an expanding universe is not like the flight of projectiles from a point. It is more like the change in the relationship between all points at once. There is no center raisin that everything moves away from. Every raisin sees itself as central, because expansion is not an explosion into a surrounding emptiness. It is a change in the distances inside the system. There is another analogy, often used but easy to misunderstand: dots on the surface of a balloon as it inflates. The surface of the balloon plays the role of the observable universe. The air around it stands in for nothing at all. It is not part of the model. As the balloon is blown up, every dot sees every other dot move away along the surface. No single dot can point to a special center on the surface where the expansion began, because in that two-dimensional space, there is no such point. The center exists only in a higher dimensional space that the dots never inhabit. The important lesson is not about balloons or bread. It is that expansion, in cosmology, is best understood not as motion through a container, but as a change in the ruler with which distances are measured, the metric of space. The rule that tells us how far apart things are once we know their coordinates evolves over time. In the early universe, that metric gave smaller distances for the same set of points than it does now. Over cosmic time, the metric has stretched. This is deeply unintuitive, because in daily life, our rulers do not grow without us noticing. If every measuring stick on Earth were to double in length overnight, but our bodies and buildings did not, we would notice immediately. But if every physical object, down to atoms and their internal forces, took part in exactly the same change, we might not notice at all. Ratios would stay fixed. Only relationships between scales that respond differently would reveal the shift. That gives a hint as to why galaxies do not themselves swell with the expansion. Gravity and other forces hold bound systems together. Within a galaxy, the mutual pull of its stars, the structure given by its dark matter halo, and the dynamics of its gas and dust form a kind of local contract that resists the general stretching of space. In smaller systems, like solar systems or planets, the binding forces are even stronger. They decouple from the large-scale expansion. Space, on those scales, is not free to grow in the same way. So when we say that space expands, we are talking primarily about distances between systems that are not gravitationally bound to each other. The gap between clusters, between large filaments, between the walls that outline cosmic voids. On those scales, the gentle outward pull of dark energy and the relic momentum of the early expansion dominate over local binding. The ruler changes, and there is nothing strong enough to insist on staying the same. There is a human echo of this. Our closest relationships, our most intense concerns, feel almost immune to the slow drift of time. Families, friendships, the habits of a day, these are like bound systems, held together by forces strong enough that the general tendency of a life to spread out, to thin, is held at bay for a while. But on larger scales, entire social worlds, cities, even cultures can move apart in ways that no one person decides. The metric of what is near or far, in human terms, changes. Places that once felt close become unreachable. The expansion is not always experienced as motion. Sometimes it is experienced as an almost invisible change in what counts as reachable at all. In cosmology, the evidence for expansion accumulates in many ways. The redshifting of light from distant galaxies is one. The faint afterglow of the early universe, the cosmic microwave background, carries another imprint. A pattern of small variations that only make sense if space has been stretching for billions of years. The distribution of galaxies on large scales matches what we would expect if tiny early ripples had been gradually amplified in an expanding medium. A single observation can be doubted. A network of them is harder to ignore. None of this tells us that expansion is easy to picture. Our minds are trained in rooms, streets, and horizons that sit inside a larger environment that appears fixed. We almost cannot help asking, what is the universe expanding into? The question is shaped by our everyday experience of growth. A wave spreads across the surface of a pond because it has more water to move into. A city expands outward because there is land around it. A balloon swells because there is air and space in the room to accommodate it. But if expansion is a change in the metric itself, the question into what begins to lose its grip. The observable universe is not a small object embedded in a larger container that we could, in principle, step outside to view. It is more like the entirety of a space whose internal distances are changing over time. The outer edge that we draw when we talk about the observable universe is not a physical wall. It is a limit on how far light has been able to travel to reach us since the beginning of expansion. Beyond that limit, there may be more of the same, or something different. The expansion does not require a pre-existing outside to grow into. It only requires that the relationships between points inside continue to change. From within, that can feel strangely similar to a personal question. When we grow, when our sense of the world stretches and our connections shift, are we expanding into something, or are we rewriting what far and near mean from the inside? There is no need for an external frame to validate the change. It is enough that what was once close now feels distant, and what was once unimaginable now lies within reach. The coordinates have not necessarily moved. The meaning of their separation has returning to galaxies. This way of thinking also quiets another common confusion. People sometimes hear that distant galaxies are receding faster than light and conclude that this violates relativity. But relativity's speed limit applies to motion through space, not to the rate at which the distance between 2 points can grow when the metric itself evolves. The raisin in the dough does not violate any local rule by finding that a very distant raisin is becoming more distant at a rate that, if naively translated to a speed through space, would exceed any familiar limit. Locally, each raisin still sees light as the fastest signal. It is the stretching of the dough in between that does the work. This distinction between local motion and global stretching is delicate, and our language fights it at every step. We are not built to think in terms of changing metrics. We reach for stories about things moving relative to a fixed background, because that is how survival works at human scales. You step aside from an oncoming car. You reach for a falling object. The background stays put, and what matters is your position within it. Expansion asks us to accept that. On the largest scales, the background itself is what changes. That shift in perspective prepares us for the role of voids. If expansion is a property of space itself, not primarily of the things inside it, then the places where there is least matter to interfere are where expansion will show its character most clearly. Dense regions cling to their own gravity. Empty regions have less to say in their own defense. They allow the metric to express itself with fewer complications. So understanding what expansion really means is not just a technical prelude. It is a way of learning to see the universe in terms of relationships rather than objects, of distances rather than just destinations. Once that habit settles in, it becomes natural to ask, in a universe where space stretches unevenly, depending on what it contains, what happens to the vast basins of almost nothing that dominate its volume? And what does their quiet compliance with expansion say about our own tendency to cling to the small bound regions of our lives, while the larger distances slip, almost unnoticed, out of our control? When you look at the universe this way, not as a stage full of moving objects, but as a shifting pattern of distances, another question appears quietly underneath the others. If space itself is changing, how exactly has matter chosen to arrange itself inside that shifting field? When cosmologists began to map galaxies in 3 dimensions, the result was not a uniform mist. It was a pattern. At first glance, it looks almost like a nervous system, or the grain of wood under old varnish, or cracks in drying mud. A web, thin threads and sheets of matter gathering into knots where the lines cross, surrounding large, dark regions where very little seems to exist. This is what people now call the cosmic web. The phrase can sound decorative, but here it is meant very literally. It is a network of matter on the largest scales we can observe. A structure where galaxies and their invisible scaffolding line up along filaments and walls, leaving most of the volume to what lies between. A filament, in this context, is not a single object, but an elongated region where galaxies and dark matter are denser than their surroundings, forming something like a faint roadway in space. A wall is a broader, sheet-like concentration of matter. The knots at the crossings are clusters and superclusters of galaxies, where gravity has pulled things together most strongly. If you zoom in, each galaxy is its own island. Rotating stars, gas, dust, a halo of unseen dark matter. Dark matter is a kind of matter that does not shine or absorb light, but reveals itself through gravity. It bends the paths of stars and gas, and even the paths of light itself, but remains invisible to our eyes and telescopes except through those effects. On the scale of the cosmic web, dark matter acts like an underlying framework. The galaxies we can see behave almost like bright decorations strung along a deeper, unseen skeleton. Zoom out, and those islands begin to trace lines. The filaments thread through space, connecting one cluster to another. Along them, gas and galaxies drift, slowly feeding the knots at their junctions. Between the filaments and walls lie voids, broad regions where galaxies are rare and dark matter is sparse. The web is not superimposed on emptiness, it is drawn along the boundaries of emptiness. It is tempting to think of the web as the main thing and the voids as the leftover gaps. But if you measure not by how many galaxies live in a region but by how much space it occupies, the balance flips. The luminous web of filaments, walls, and nodes fills only a small fraction of the universe's volume. The rest is taken up by voids. The pattern is not stuff with a few holes, it is emptiness with a fragile, connected outline. In a way, this should not be surprising. Imagine a sponge. Most of the volume is air. The solid part is a thin network of material, wrapping around cavities and channels. Or think of foam on the surface of water, where bright borders surround dark pools. The cosmic web has a similar character, but on scales where each bright bubble wall is made of galaxy clusters instead of soap. And each dark interior is not a pocket of air but a region of almost nothing. What gives this web its shape is contrast. In the early universe, matter was spread with only tiny variations from place to place. Over time, gravity amplifies those differences. Regions that start slightly denser pull in more material, becoming filaments, sheets, and nodes. Regions that start slightly emptier lose matter to their neighbors, becoming voids. The web grows out of this uneven tug-of-war. It is not drawn by hand from outside. It emerges from the simple rule that gravity likes to collect. The cosmic web is also where the history of expansion leaves its marks. As the universe stretches, matter has to decide how to respond. Where gravity is strong, as in clusters and thick filaments, it slows the local expansion, and sometimes even reverses it, holding galaxies together. Where gravity is weak, as inside voids, the general expansion wins. Those regions stretch more quickly, becoming larger and emptier over time. The web is the trace of this unequal evolution, dense threads clinging together while the surrounding spaces thin and widen. From our position inside a galaxy, in a small group on the edge of a filament, this global geometry is hard to feel. We live in one bright strand. Our night sky is dominated by the stars of the Milky Way, then by a sprinkling of nearby galaxies. It takes a deliberate effort to imagine that, on scales far beyond what we see. Our home sits like a tiny knot on the margin of a great basin. The nearest truly empty stretches are so large that no journey we can make would cross them. Yet, on the map, they are the dominant feature. There is a quiet unease in realizing this. Everything we know, every story ever told, arises from a node in a web that is itself the border of an absence. Our sense that the universe is full of galaxies is a kind of bias, based on where we have to stand in order to exist at all. Life, as far as we can tell, needs the dense regions, stars, planets, heavy elements forged in past explosions. Consciousness wakes up in the knots, not in the voids, and so it tells its stories from there. The web also has a kind of precariousness. The filaments are not thick, permanent beams. They are more like rivers, constantly fed by the flows of dark matter and gas, but also constantly eroded by the very expansion they outline. Matter moves along them toward the nodes, and as time goes on, those streams thin. If you imagine the future stretched far ahead, the threads grow longer and more fragile. The connections fewer, islands of bound structures may remain, but the pathways that once linked them fade into barely perceptible traces against an ever larger sea of isolation. In that sense, the cosmic web is a temporary compromise between gravity and expansion. Gravity draws lines, building skeletons of matter. Expansion tries to pull everything apart, smoothing differences. For a long cosmic interval, neither side wins completely. The result is this delicate network, a three-dimensional drawing of where matter has found a way to stay together. Even as the underlying fabric stretches, the term large-scale structure is sometimes used for this pattern. It sounds dry, almost architectural. But what it really points to is the fact that, once you look beyond individual galaxies and clusters, there is a deeper order in how the universe is arranged. That order is not rigid, and it is not designed. It is dynamic, constantly evolving. Yet it is coherent enough that you can talk about filaments, walls, and voids as if they were features of a single object. The methods we use to reveal that order are themselves an interesting part of the story. Galaxy surveys, for example, measure the positions and motions of many galaxies across the sky, turning faint points of light into a three-dimensional map. Each galaxy's light is stretched or compressed by its motion relative to us, a shift called redshift when the light is pushed toward longer wavelengths. Redshift acts as a kind of distance indicator, not perfect, but good enough that, when you combine millions of such measurements, the underlying structure begins to emerge. Other techniques look not at the galaxies directly, but at their gravitational influence. Light passing near a concentration of matter is bent slightly, an effect known as gravitational lensing. By measuring subtle distortions in the shapes of many background galaxies, astronomers can trace the distribution of dark matter that is otherwise invisible. These lensing maps, when combined with galaxy surveys, confirm that the visible web of galaxies truly rides on top of a deeper, dark skeleton. On even larger scales, the patterns in the faint microwave afterglow of the early universe give a kind of blueprint. Tiny variations in temperature and density in that early light grow, over billions of years, into the filaments and voids we see today. Simulations that start from those early fluctuations and let gravity and expansion run their course naturally produce something that looks like the observed cosmic web. It is one of the places where the mathematics of cosmology and the images from telescopes line up in a way that feels quietly persuasive. All of this might sound very far from human experience. Yet there is a familiar sensation hidden in it, the idea that structure lives mostly along boundaries, that most of any space is taken up by what we do not occupy, that connections are threads stretched across great gaps. These are not only cosmic truths, they echo in social networks, in emotional lives. In the way ideas hang together, we often imagine our world as densely filled with meaning, as if the important parts of a life were packed side by side. But when you examine it closely, much of what gives shape to a life happens along edges, at the borders between one phase and another, at the narrow channels where paths cross. In the rare moments when separate stories touch, between those moments lie voids of routine or quiet or uncertainty that, in retrospect, occupy most of the volume. The personal web looks thick from the inside, but when you step back, it is filaments and nodes suspended in a larger, less structured space. The cosmic web invites us to see the universe in that same relational way, not as a warehouse filled with independent objects, but as a network whose meaning lies in connections, contrasts, and the empty regions that surround them, matter. In this picture is the tracing of an outline, not the whole drawing. Emptiness does not merely surround the web, it defines the spaces in which the web can exist. And if the universe is, on its largest scales, mostly a framework sketched around vast regions of almost nothing, then the next questions become sharper. How do those empty regions grow as expansion accelerates? How does the web thin and rearrange itself as the balance between gravity and the stretching of space shifts over time? What happens to a universe where the threads that once tied it together slowly erode, leaving most of reality not just unoccupied, but unreachable? Before the threads could fade, they had to be noticed at all. And that meant learning to see not only what was drawn on the map, but also the regions that refused to be filled in. The story of the voids begins not with confidence, but with doubt about whether the holes were even real. The early attempts to chart the universe in 3 dimensions were modest by today's standards. Astronomers gathered light from galaxies, measured how much their spectra were shifted toward the red, and turned those shifts into rough distances. A spectrum is like a barcode of light, a pattern of dark and bright lines that reveals what elements are present and how the light has been stretched. Redshift, in this context, is the amount by which those lines move toward longer wavelengths, carrying the imprint of motion and of cosmic expansion. Each galaxy became a point in a growing catalogue. Plotting those points in space was like turning a flat star chart into a scattered, 3-dimensional cloud. At first, the datasets were small, the sky coverage patchy. When a region looked underpopulated, the natural assumption was that the telescope simply had not looked carefully enough, or that dust, clouds, or instrumental limits had hidden some of the galaxies from view. Astronomers have a name for this kind of problem: selection effects. A selection effect is a bias built into the way you choose or detect your object. If your survey is less sensitive in some direction, or if it misses faint galaxies beyond a certain distance, your map will show apparent gaps that are not really part of the universe, but part of your method. It is a reminder that a map can reflect the structure of your tools as much as the structure of reality. So, when early redshift surveys began to show surprising holes, large stretches of space with very few plotted galaxies, many people were cautious. The simplest explanation was that these were artifacts. The telescope may have been pointed there for less time. The galaxies may have been fainter than the detection limit. The algorithms that turned spectra into distances might have discarded ambiguous cases. The emptiness, in other words, could be a trick of the gaze. Then some of the holes refused to go away. One of the most famous early examples lay in the direction of the constellation Boötes, a patch of sky in the northern hemisphere. When astronomers measured galaxy distances in that region, they found a vast volume with far fewer galaxies than expected. It was not just a small gap that could be blamed on incomplete sampling. It spanned hundreds of millions of light-years across, a cavern in the distribution. Other teams, using different instruments and strategies, looked again. The emptiness persisted. To call such a structure a void is already to take a step away from skepticism. A void, in everyday language, sounds like something definite, a region that is actively empty. But in cosmology, the definition is more careful. A cosmic void is a region where the density of matter, especially in the form of galaxies and dark matter, is significantly lower than the cosmic average. It is not an absolute vacuum. There are still stray galaxies, thin gas, weak magnetic fields, a faint bath of radiation passing through. What sets it apart is that, compared to its surroundings, it is starved of structure. As more galaxy surveys were conducted, the picture sharpened. Different telescopes, in different hemispheres, using different selection criteria, all began to reveal the same basic pattern: a network of filaments and walls enclosing large, underdense regions. The voids were not random. They were connected, sometimes merging into even larger cavities. The details depended on the survey, but the existence of the emptiness did not. At a certain point, it became harder to maintain that all of these gaps were accidents of observation. There is a subtle shift here, from treating the voids as suspicious absences to recognizing them as part of the structure to be explained. That shift has an echo in ordinary life. There are times when we assume that the quiet parts of our days, the unremarkable stretches, are just missing data, nothing to notice. Only later, perhaps, do we realize that those intervals have a shape of their own? Patterns of avoidance, invisible boundaries, spaces in which decisions could have been made but were not. The voids in a life can be as telling as the events that fill it. In cosmology, once the voids were taken seriously, they became a tool. By measuring how empty they are, how they are distributed, and how they evolve, researchers could test models of how matter clumps and how expansion proceeds. The fact that voids grow over time, their interiors diluting as matter flows outward toward the surrounding walls, is not just a curious feature. It is a consequence of how gravity and cosmic expansion work together. But before they could be used that way, cosmologists had to build a language to describe them. Defining a void is not as simple as finding a region with no galaxies at all. Data are always incomplete. Noise, always present. Instead, algorithms were developed to search for underdense zones in the galaxy distribution, grouping together neighboring regions where the density falls below a chosen threshold. Different methods draw different boundaries, but they converge on the idea that voids are extended, coherent, low-density regions, not isolated pockets of missing points. Large computer simulations, which follow the motions of dark matter and gas under the influence of gravity and expansion, added another layer of evidence. When these simulations start from a nearly uniform early universe, with small random fluctuations in density, and are allowed to evolve, they naturally produce a web of filaments and voids that resembles the observed one. The voids in the simulations have similar sizes, shapes, and alignments to those in the maps derived from galaxy surveys. The holes in the data were not just errors, they were predictions. Still, the process of accepting voids as structural foundations, rather than as nuisances, was gradual. Scientific habits often favor what can be clearly seen and counted. Clusters of galaxies, with their hot X-ray emitting gas and strong gravitational lensing, present themselves as obvious laboratories for astrophysics. Voids are more like negative space in a drawing. To study them, you have to trust that what is missing is as meaningful as what is present. There is a certain discomfort in making absence an object of study. It asks you to pay attention to what is not there, to infer from silence. That can feel risky, both scientifically and personally. Yet in both realms, patterns of absence often tell truths that presence alone cannot. Which parts of the sky never host rich clusters? Which topics never arise in a conversation? Which memories never seem to form? The empty regions are not merely blank. They outline the structure of what is allowed. As void catalogues grew, some early skepticism turned into a kind of appreciation. Here were regions where the usual complications of crowded environments were minimized. No swarming galaxies tugging on one another. Very little gas to cool and collapse. The gravitational field is smoother, the expansion more free. If you want to see how dark energy behaves in relative isolation, or how the large-scale expansion rate may vary across different environments, voids become natural laboratories. The phrase structural foundation is apt, but slightly misleading if it suggests solidity. Voids are foundational not because they are made of something firm, but because everything else is arranged around them. The cosmic web, with its filaments and walls, is shaped as much by the growth and merger of empty regions as by the collapse of dense ones. As underdense patches expand and join, they squeeze matter into the spaces between them, carving out the very structures that first drew our attention. Seen in that light, the skepticism about voids was not a trivial obstacle. It reflected a deeper reluctance to grant emptiness a causal role. It is easier to say that things happen because something is there than because something is not. But the universe does not share that preference. On the largest scales, what is missing exerts a kind of authority over what remains. The slow recognition of that fact, in cosmology, mirrors the quieter recognitions many people arrive at in their own lives, that the paths not taken, the words not spoken, the spaces left blank on purpose or by neglect, are not mere background. They frame the web of what actually occurred. By the time voids were firmly integrated into the standard picture of large-scale structure, they had already begun to change the kinds of questions cosmologists asked. No longer were they just curiosities or problems to be explained away. They became part of how we describe the universe at all, a vast collection of underdense basins, separated by a thin, luminous framework. From here, it is a short step to a more unsettling thought. If the universe is so dominated by these regions of almost nothing, then perhaps the true arena of cosmic expansion, and the key to its future, lies not in the crowded knots where we live, but in the immense, quiet spaces where almost nothing ever forms. If the truest arena of expansion lies in the places where almost nothing forms, then the next quiet question is simple and unsettling. How empty is that? Almost nothing. Really? A cosmic void sounds absolute. The word suggests a region scraped clean of matter. A place where there is literally nothing. In everyday language, we use empty in that way all the time. An empty room, an empty glass, an empty road at night. But even those things are not truly empty. The room has air. The glass has light and dust and temperature. The road has distant noise and the faint smell of fuel. Empty is always an exaggeration we allow ourselves. Cosmic voids are no different. They are not places where existence stops. They are places where, by the standards of the universe, structure has almost given up. To say that in a precise way, cosmologists use the idea of density. Density is simply how much stuff you have in a certain amount of space. You can imagine taking a large box of fixed size and counting how many galaxies fall inside it. Then you slide that box to a new location and count again. In some places, the count is high. In some places, low. If you average over many positions, you get a mean density for the universe on those scales. A void is a region where, when you place that box almost anywhere inside, you get a count much lower than that mean. In practice, astronomers often describe this difference as a density contrast, how far below the average a region falls. A typical void might have only about 1/10 to 1/5 of the mean number of galaxies per unit volume, sometimes even less. depending on how strictly you define it. That means that, compared to a typical patch of the cosmos, a large void has surrendered most of its galaxies to the walls and filaments surrounding it. To get a sense of scale, imagine the distance between bright galaxies in a relatively crowded region, like a cluster, as being something like a short hop in a plane from one city to another, inside a large void. The distances between similar galaxies can swell to something more like the span of entire continents, or more. You could travel for hundreds of millions of light years in a straight line and never pass close to a galaxy as bright as our own. There would still be faint dwarf galaxies here and there, like isolated villages. But the dense cities would be gone. The emptiness goes deeper than galaxies. Dark matter, the invisible substance that makes up most of the mass in the universe, is also scarce in voids. In the standard picture of structure formation, dark matter forms the backbone on which galaxies assemble. Where there is less dark matter, the gravitational wells are shallow, and gas has a harder time collapsing to form stars. So a void is underdense not just in the things we can see, but in the hidden scaffolding that would allow more visible structure to grow. It is a double emptiness, few lights, and very little framework to hang new lights on. The word isolation starts to become literal here. A galaxy, living deep inside a large void, is far from its nearest peers. It is unlikely to collide or merge with other big galaxies, events that in denser environments are common and important in shaping galactic growth. Its supply of fresh gas may be limited, cut off from the filaments that feed galaxies in the cosmic web. Over long stretches of cosmic time, such a galaxy can age almost undisturbed, forming stars at a slow pace, quietly dimming as its brightest stars burn out and are not fully replaced. There is a strange tenderness in that picture. A single island of matter, adrift in a region where almost nothing else has condensed, slowly using up the possibilities available to it. No grand interactions, no dramatic inflows from bustling neighbors, just a long, thinning present. If you imagined consciousness arising in such a place, its sense of the universe might be of a vast, silent, stable environment, with little hint of the networks and collisions that characterize the denser web. Its cosmology, if it ever tried to build one, could easily underestimate how rough and busy the universe is elsewhere. To describe how empty a void is, though, you cannot rely on single examples. You need statistics. That is why cosmologists build void catalogs, lists of voids identified in survey data, with estimates of their sizes, shapes, depths, and locations. Different algorithms find slightly different sets of voids, because they draw the boundary between inside and outside in different ways. Some methods treat galaxies as markers and look for regions where the spacing between them becomes unusually large. Others smooth the matter distribution over a grid and search for basins in that smooth density field. All of them, in one way or another, ask the same question. In which regions does the universe fail to build its usual amount of structure? The answer is surprisingly consistent. On very large scales, most of the cosmic volume belongs to underdense regions. The cosmic web is a kind of lace wrapped around these basins. We tend to name the lace and ignore the holes. But the holes occupy more space. When you hear that most of the universe is empty, this is what is meant. Not that there are no particles or fields, but that most of space is far below the density needed to form rich, complex structures. It is worth pausing on what most means in this context. If you were to choose a point at random in the vast three-dimensional volume of the universe, you would be far more likely to land in a void than in a filament or cluster. High-density regions are rare and small, but loud. Low-density regions are common and large, but quiet. Our attention follows the loudness, not the probability. This has a personal analog. If you try to remember a year of your life, What comes first are the bright points, a crisis, a celebration, a beginning, an ending. Those are the clusters of experience. But if you were to pick a random moment from that same year, most likely you would land in something more ordinary. A commute, a meal, a half-forgotten conversation, a solitary walk between obligations. The lived volume of a life is filled mostly with such underdense moments. The intense events are real, but they are not the dominant environment. Returning to the cosmos, there is another subtlety. Even in voids, the fabric of spacetime is not uniform. The underdensity creates its own gravitational pattern. Because matter is scarce, the local gravitational pull toward the center of a void is weaker than average, while the surrounding walls, being denser, pull matter outward from the void's interior. Over time, this imbalance means that matter tends to flow from the inside of voids toward their edges. The voids effectively evacuate themselves, becoming emptier as the universe ages. This evacuation is gentle, stretched over billions of years. But its outcome is dramatic. Voids grow. Small, underdense patches merge into larger ones. As they do, they squeeze the surrounding web into thinner structures. In the language of fluid flow, voids are like expanding bubbles in a fluid, pushing the fluid into the regions between them. Except here, the fluid is the sum of all matter that can clump and shine. From the point of view of expansion, voids are also where the influence of dark energy is least resisted. Dark energy is a term for whatever is causing the cosmic expansion to accelerate rather than slow down. It acts, as far as we can tell, like a property of space itself, present even where there is no matter. In dense regions, gravity counters its effect. In voids, gravity is weak, and dark energy has comparatively freer reign. You can think of voids as the places where the universe leans most fully into its tendency to grow. Cosmic isolation, then, is not just about distance from neighbors. It is also about being in a region where the general behavior of the universe is most exposed. A galaxy in a void is not only alone, it is carried along by an expansion that has fewer local complications. It is, in a way, closer to the pure background behavior of the cosmos. There is a quiet echo here for anyone who has experienced long stretches of solitude. When you are far from the dense networks of social life, some things become harder. Support, surprise, collision with other trajectories. But something else becomes clearer: the slow, underlying tendencies of your own mind. The background patterns that are usually masked by constant interaction. Isolation is not only a lack, it is also an environment where certain dynamics, otherwise hidden, are allowed to unfold. For cosmologists, voids are becoming that kind of environment. By measuring how empty they are, how fast they expand relative to the average, and how they distort the paths of light and matter around them, researchers can test the laws that describe gravity and dark energy on the larger scales. The answer to how empty is a void is no longer just very. It is a set of numbers and relations that must be satisfied if our picture of the universe is to hold. But beneath the measurements, the basic insight persists. A void is not a mistake. It is not a hole waiting to be filled. It is a stable feature of a universe where matter was never evenly shared, and where the majority of space never had enough to build with. To understand the cosmos, we are forced to take seriously a place where almost nothing happens, stretched over expanses so large that, for any inhabitant, the rest of the universe would feel not just distant, but fundamentally out of reach. The thought that most of reality may be out of reach invites another, quieter one. Was it always meant to be this way? Or did the emptiness grow into its role from something far less dramatic? To answer that, we have to go back to a time when the universe did not yet have filaments, or galaxies, or even atoms. Only a hot, dense, almost uniform sea of energy and particles. Almost uniform, but not quite. In that early state, the universe was filled with tiny irregularities. Some regions were a little denser than average, some a little emptier. The differences were small, far too small to see directly with any kind of eye, but not zero. Those minute imbalances are the origin of everything that would later become structure, including the voids. The usual way to describe these early irregularities uses the language of quantum theory. Quantum fluctuations are the restless, unavoidable variations that appear even in what we would otherwise call a vacuum. In classical thinking, emptiness is stable. In quantum thinking, fields that fill space are never perfectly still. They quiver, they fluctuate, they borrow energy for tiny moments and then give it back. These fluctuations are small, but they are everywhere. In the very early universe, there is good reason to think that such fluctuations were stretched by a brief and violent episode of accelerated expansion, often called inflation. Inflation is the idea that, for a very short time near the beginning, the universe expanded much faster than it does now, smoothing out most irregularities and blowing up quantum wiggles to cosmic scales. What would have been microscopic differences became, under this enormous stretching, slightly denser and slightly emptier regions spanning light years, then thousands of light years, then more. You can picture this in a rough way. Imagine a sheet of rubber with tiny wrinkles, too small to notice. If you suddenly stretch the sheet by an enormous factor, those wrinkles widen. Each little hill, each little valley, becomes a broad, gentle rise or dip. The sheet looks almost smooth, but not perfectly. That almost, those small leftovers, are enough. The early universe, after inflation, was like that stretched sheet, but in 3 dimensions and with gravity ready to respond. Every slightly denser patch had just a bit more mass to pull on its surroundings. Every slightly emptier patch had just a bit less. As the universe continued to expand and cool, these differences grew. The denser regions slowed their expansion relative to the background and began to draw in more matter. The emptier regions did the opposite. They lost matter to their surroundings and became even more underdense. In that sense, voids and clusters share a common origin. Both start as mild deviations from the average. One type grows by accumulation, the other by evacuation. Gravity amplifies both directions. Where there is a little more will gather. Where there is a little less, more will leave. The first clear sign we have of these early patterns comes from the cosmic microwave background, the faint afterglow of the hot early universe. This light has been traveling for billions of years. Since the universe cooled enough for electrons and protons to combine into neutral atoms and let light move more freely, imprinted on that glow are tiny variations in temperature and brightness, corresponding to regions that were slightly denser or emptier at that time. Those variations are small, just a tiny fraction difference from place to place, but they trace the seeds of all later structure. Where the glow is slightly hotter or colder, the matter density was slightly higher or lower. Over immense stretches of time, those initial gentle ripples evolve into the web of filaments, clusters, and voids we see now. The map of the present universe is, in that way, a stretched and transformed version of the pattern encoded in that ancient light. In large-scale simulations, cosmologists take these early fluctuations, as measured from the cosmic microwave background, and let them grow under the rules of gravity and expansion. The result, after billions of years of simulated time, is a universe filled with a cosmic web and extensive voids that look remarkably like those we infer from galaxy surveys. It is a form of replay. The emulator does not know about galaxies or observers. It knows about mass, motion, and the shape of spacetime. From that alone, the pattern emerges. At first, The differences between denser and emptier regions remain modest. The universe is young, and expansion is rapid. Matter does not have much time to rearrange. Gradually, as expansion slows under the influence of gravity, the clumping accelerates. Denser regions begin to collapse, forming the ancestors of galaxies and clusters. Emptier regions, by contrast, thin out. They do not collapse, they relax. Matter drains away along the directions where the gravitational pull is strongest, often toward emerging filaments and walls. This is why voids tend to have shapes that are not perfectly spherical. They are stretched and sculpted by the surrounding structures. Just as rising bubbles in a fluid are distorted by currents and obstacles, over time, smaller voids can merge to form larger ones, their boundaries shifting as the surrounding web rearranges. The emptiness is not static. It grows, fuses, reshapes itself. There is an interesting asymmetry hidden in this process. Dense regions can only collapse so far before internal pressures, rotation, and other forces halt or slow the fall. Galaxies form, stars ignite, black holes grow, but the matter does not compress indefinitely everywhere. Emptiness, on the other hand, has no such limit. There is no minimum density required by any law. The matter can keep flowing out, leaving behind regions that are ever closer to true vacuum. In that sense, there is more room for emptiness to deepen than for matter to condense. If you step back from the technical language, there is a familiar pattern here. Small, random differences at the beginning lead, over time, to stark inequalities. Some places end up crowded and complex. Others end up almost bare. Nothing in the initial conditions singled out particular points as destined to be rich or empty. The differences were tiny and spread everywhere. Yet under the right dynamics, those tiny biases are enough to build a world where most of the volume belongs to absence. There is a human mirror to that, though it is not exact. Lives, too, begin under conditions that may not seem dramatically skewed at first glance, at least when viewed from very far away. Small advantages, small lacks, barely noticeable at the time, can grow through repeated reinforcement into large disparities. Some trajectories become dense with opportunities, encounters, and consequences. Others open into long intervals where very little seems to accumulate. It is not that the universe decides in advance which path should be full or empty, but the rules for how small differences grow can make the end result feel as if it was set in stone from the start. In the cosmic case, the rules are written in gravity and quantum fluctuations and the expansion of space. In the personal case, they are written in social structures, chance meetings, habits, and fragile choices. In both, there is a sense in which emptiness is not simply what remains when something fails to appear. It is what emerges when many small flows all point away. Returning to cosmology, one of the striking results of this picture is that voids are not accidents layered on top of an otherwise uniform expansion. They are natural products of the same processes that form galaxies. Every quantum fluctuation that inflation stretched into a slightly underdense region has the potential to become part of a void. The underdense patches are not mistakes. They are as fundamental as their overdense counterparts. This means that when we look at a large void today, we are seeing not just an absence, but the fossilized trace of an early low point in the density field. That region began lower than average and spent the entire history of the universe falling further behind. It never had enough mass to keep up with the race toward complexity. Each epoch widened the gap. You could think of such a region as the universe's way of remembering its own early unevenness. The rich clusters remember the early peaks. The voids remember the early troughs. Neither is more authentic than the other. Both are outcomes of the same initial restlessness. There is another layer, quieter but important. The role of dark energy, the mysterious component driving the current accelerated expansion. becomes more prominent as the universe ages. When the universe was very young and dense, ordinary matter and radiation dominated its behavior. Gravity kept the expansion in check, even if it could not reverse it globally. As the universe thinned, dark energy came to matter more. Its effect is to cause expansion to accelerate rather than slow down, in regions that are already underdense, where gravity is weak. This acceleration has relatively less opposition. The metric there can stretch more freely. Voids, seeded by quantum fluctuations and shaped by gravity, become the places where dark energy's influence is most unmasked. They are not just old scars of early randomness, but active arenas where the present and future behavior of the universe plays out with fewer distractions. From this point of view, the origin of voids is not a story about a single moment long ago. It is a continuous story that begins with microscopic uncertainty, passes through inflation and the hot early plasma, and continues through billions of years of gravitational sorting and accelerated expansion. Emptiness is not given once. It is built and rebuilt, magnified, deepened. The unsettling consequence is that, in a universe like ours, large regions of almost nothingness are not anomalies to be fixed. They are the dominant outcome of the simplest rules we know. If you start with an almost uniform sea of tiny fluctuations and let it evolve under gravity in an expanding spacetime, you do not get a universe that is mostly filled with luminous, dense structures. You get a universe where such structures form a thin web, and most of the volume relaxes into near silence. Standing inside one of the bright knots, it is easy to imagine that the universe is about galaxies, stars, and the stories that unfold on small, hospitable worlds. The origin of voids suggests another reading, perhaps, on the largest scales. The universe is about the way absence spreads from microscopic uncertainty into macroscopic fate, leaving scattered islands of complexity floating in a sea whose most enduring feature is that almost nothing ever happens there at all. If the universe is, on its widest scales, a story about how absence spreads and settles, then a quieter question waits underneath. Why does that absence win so completely over everything else? One way to approach this is almost childlike in its simplicity. Imagine that you could close your eyes, spin around, and drop a pin at random somewhere in the vast three-dimensional volume of the universe. Not in the sense of choosing a random galaxy, but a random location in space itself. Where would you land? Not in a galaxy, not in a cluster, not even in a filament. Almost every time, you would find yourself in a void. This is what it means for voids to dominate by volume. The luminous structures that fill our images and textbooks take up very little of the available space. They are dense, but they are thin. They carry a large fraction of the matter, but not a large fraction of the geometry. The voids, by contrast, carry very little matter, but most of the space. If you weigh the universe, matter wins. If you measure it, absence does. It is easy to miss how radical that is. Our sensory habits are tuned to what is nearby and bright. A single star in the night sky feels like an enormous presence, even though between that star and its neighbors lie expanses so large that the star might as well be a dot on a sheet of nearly pure emptiness. A city at night looks full when you stare at the windows. You have to step back and look at the dark between the buildings to realize how much of it is air. On cosmic scales, the same trick of attention plays out. Cluster catalogs grow thick. Surveys log countless galaxies. The mind begins to think of the universe as crowded. Only when you switch from counting objects to sampling points in space does the balance flip, and the voids step forward as the main environment. This imbalance is not static. Voids do not merely sit and wait between filaments. They evolve. Under the combined influence of gravity and cosmic expansion, underdense regions expand faster than the universe as a whole. Their internal density falls. Their boundaries push outward, and their shapes blur and merge. Dense regions, by contrast, expand more slowly or even collapse inward, binding into clusters and superclusters. You can picture the cosmic web as a kind of compromise surface between many growing bubbles of emptiness. Each void swells, and in doing so, it nudges matter toward the places where other voids are also pushing. Those squeezed regions become walls and filaments, where several such flows converge. Knots form. The web is the shared boundary of many expanding absences. As time passes, the voids do not simply grow uniformly. Smaller ones can be crushed by the collapse of surrounding overdense regions, their identity erased as they are consumed by clusters or walls. Others survive and expand, fusing into larger basins. There is a hierarchy in emptiness. Just as there is a hierarchy in structure, tiny hollows give way to grand cavities. In this quiet competition, the largest voids slowly take over the story. Their interiors dilute, asymptotically approaching an almost perfect vacuum. Their outward growth stretches the web thinner. Filaments that once conveyed matter between massive nodes become more tenuous. Some connections break entirely, leaving clusters isolated, like beads separated when a thread wears through. The dominance of voids, then, is not just a snapshot fact about how much volume they occupy right now. It is a direction in which the universe is moving. Volume flows toward emptiness. Structure retreats into shrinking refuges. There is a sense in which this is simply geometry. If you imagine a foam of bubbles expanding in a box, the total volume is always the sum of the bubble interiors and the thin films between them. If the films thin without breaking, the bubbles grow. Over time, a random point is more and more likely to lie in the interior of some bubble, far from any boundary. Something similar happens in the cosmic case, except that the box itself is expanding, and the films are made of matter. Yet this geometric view leaves something out. The dynamics have a source. They are not just the byproduct of initial conditions. They are driven, in the present epoch, by the fact that cosmic expansion is accelerating. The more space there is, the faster new space appears between unbound regions. A small underdensity is like a slightly lower crest in a rising tide. As the water level climbs, that patch deepens into a basin. Given enough time, the basin becomes a gulf. The standard cosmological picture predicts that this acceleration will continue. The component we call dark energy, which behaves as if it were a persistent property of space itself, does not dilute as matter does. As the universe expands and matter thins, dark energy maintains its density. Eventually, it dominates the large-scale behavior completely. Gravity can still hold already bound structures together, but it cannot recruit new members across widening chasms. The consequence is a slow dissolution of the cosmic web, not in the sense that galaxies tear themselves apart, but in the sense that the network of connections between distant structures fades. Groups of galaxies that are tightly bound, like our own local collection, remain intact, or even merge into single larger galaxies, but more distant clusters, which are not gravitationally bound to us, retreat beyond any possibility of new contact. Light emitted from them after a certain time will never reach us. They cross a kind of horizon, not of space, but of causality. From inside one such bound island, the sky would gradually empty of distant galaxies. One epoch would show rich filaments and clusters. A later one would show fewer. Eventually, only the local structure would remain visible, surrounded by a darkness that is not absolute, but effectively unreachable. The universe, as experienced from that island, would come to look small and self-contained, even as its true extent and history remain vast. The dominance of voids, in this future, is not just a matter of statistic. It becomes a limitation on what can be known. Most of the cosmic web will slip forever outside any possible observation from any given island. The record of large-scale structure, of early patterns, of the shared history of matter, will be cut off. An observer living deep in that future would find themselves in a quiet, apparently static environment, with very little evidence that the universe was ever different. There is something unsettling in that prospect. Cosmology, as we practice it now, occupies a special era. The cosmic web is still richly connected. The light from distant structures still reaches us. The microwave afterglow of the early universe is still visible, stretched into radio wavelengths, but intact enough to read. We live when the record of both the dense and the empty can be gathered into a single story. In the far future, that will no longer be the case. The same expansion that created room for structure will, when driven hard enough by dark energy, erase the evidence of its own past. The voids will not only dominate volume, they will also dominate what is accessible to thought. The universe will be mostly isolation, not just in fact, but in experience. It is hard not to feel a faint echo of this on smaller scales. As lives unfold, connections that once seemed permanent can slowly thin. Friendships that were part of a dense social web become occasional messages, then distant names, then silences. Communities fracture under pressures no single person controls. New ties form, but always within a shrinking, effective horizon of attention and memory. A person may reach an old age in which their world has contracted to a small cluster of familiar faces and places, while vast regions of their own past existence lie beyond recall. The void in that sense is not death, but distance. None of this is an argument that the universe, or a life, is meaningless. It is a description of how structure and emptiness share the same stage, and of how, given enough time, emptiness tends to claim more of it. The patterns we care about are local against that background. Their significance does not come from how much volume they occupy, but from what happens inside them. Still, knowing that most of reality is, and increasingly will be, made of regions where almost nothing ever happens, changes how we place ourselves. It also sharpens the role of voids in cosmology itself, because they expand more rapidly and are less cluttered by non-linear gravitational interactions. Voids are sensitive probes of the underlying rules that govern cosmic acceleration. Small deviations from the standard laws of gravity, or from the behavior expected of dark energy, can manifest as subtle differences in void size, shape, and growth over time. In that way, the regions where there is least matter become the places where the universe reveals most clearly how it intends to evolve. We usually think of experiments as things we do where matter is dense and controllable. Laboratories, particle accelerators, telescopes pointed at bright sources. Voids invert that instinct. They are laboratories made of absence. Their very lack of complexity makes them clean environments in which to test ideas about the large-scale behavior of spacetime. When we measure how galaxies on the edges of voids are pulled outward, or how light from background sources is distorted as it passes through these underdense basins, we are listening to the universe explain its own future. The phrase "cosmic fate" can sound melodramatic, as if the universe were a character in a play. In practice, it means something more modest, given the ingredients we observe and the laws that seem to link them. What patterns do we expect to see as time goes on? In the current picture, that fate is one of increasing emptiness, fragmentation of the web, and isolation of bound islands. No collision, no sudden catastrophe, just a slow, persistent preference for separation over connection. From our perspective, now, that fate is not an immediate threat. The timescales involved are far beyond any human history. Stars will burn for ages before the sky empties in the way described. But on the scale of the universe itself, the direction is already clear. The dominance of voids in volume today foreshadows their dominance in experience tomorrow. Some people find this bleak. Others find it oddly calming. Either way, the universe does not adjust its behavior to suit those reactions. It continues to let matter clump where it can, and to let absence spread where it must. Our role, for as long as we can hold it, is to notice both. And behind all of this, there remains one more question, still unresolved. The growth of voids, the thinning of filaments, the acceleration of expansion, all lean on something that, for now, is only named, not understood, dark energy, a term that states there is a cause, without yet telling us what that cause is. To understand why the future belongs so thoroughly to emptiness, we have to look more closely at that invisible pressure, and at why its influence seems to live most fully in the places where there is almost nothing at all. If the future of the universe belongs to emptiness, then somewhere inside that future there must be a quiet engine, pushing gently, everywhere at once. We give that engine a name, but a name is not an understanding. The story of dark energy begins with a surprise that should not, at first, have been there. For a long time, cosmologists expected that the expansion of the universe would be slowing down. Gravity pulls. Every galaxy tugs on every other, every cluster on every cluster. Even if the universe kept expanding forever, the expansion ought to have been gradually losing speed, like a ball rolling uphill. To test this, astronomers turned to a particular kind of stellar explosion called a Type 1, a supernova. The name sounds technical, but the idea is simple. These are explosions that, under many conditions, reach roughly the same peak brightness. Because of that, they can be used as standard candles. If you know how bright something truly is, and you measure how bright it appears, you can estimate how far away it lies. It is like knowing the wattage of a light bulb and inferring its distance from how strong the glow looks. By finding these supernovae in distant galaxies and measuring how their light had been stretched by cosmic expansion, astronomers could reconstruct how the expansion rate had changed over time. The expectation was clear. The more distant, and therefore the earlier in cosmic history, the faster the expansion should have been. What they found instead, in the late 1990s, was the opposite. The distant supernovae were dimmer than expected. They appeared farther away than they would be in a universe whose expansion was steadily slowing. The only consistent reading of the data was that, on large scales, the expansion had started to speed up. The universe was not coasting. It was accelerating. Acceleration needs a cause. In our everyday experience, to accelerate something, you push or pull it. The cosmic case is more subtle. On the scale of the universe, the usual forms of energy and matter, with their positive mass, tend to slow expansion, not speed it. What was needed, in the equations that describe spacetime, was something with a kind of negative pressure, a gentle outward push that does not dilute as the universe grows. We call that something dark energy. The word dark does not mean evil or hidden with intention. It simply means that it does not emit or absorb light in any detectable way. The word energy is equally cautious. It signals that this ingredient enters the equations in the slot usually occupied by energy and matter. But its nature remains uncertain. It might be a property of the vacuum itself, a cosmological constant, unchanging over time. It might be a dynamical field, slowly evolving. For now, the data tell us more about its effect than about its identity. One feature stands out. Dark energy appears to be remarkably uniform. Unlike matter, it does not clump into stars or galaxies. It does not trace the filaments of the cosmic web. It fills space almost evenly, like a background tension in the fabric of spacetime. That has a crucial consequence. The more space there is, the more total dark energy there is. but its density per unit volume stays roughly the same. That behavior is the key to acceleration. As the universe expands, the density of matter drops. Galaxies move farther apart. The same amount of mass is spread over a larger region. Dark energy, by contrast, maintains its density. As the universe grows, its relative importance increases. Eventually, it dominates the large-scale dynamics. The outward push wins over the inward pull. This is where voids become the clearest mirrors. In regions dense with matter, gravity partially cancels the push of dark energy. Bound structures like galaxies and clusters do not participate directly in the accelerated expansion. Their internal dynamics are governed by local mass, not by the overall stretching of space. Within them, orbits and collisions continue with little reference to the global trend. In voids, almost none of that is true. There is less matter to pull things together, fewer bound structures to carve out exceptions. The local gravitational field is weak. That means the contribution of dark energy to the behavior of those regions is comparatively larger. The metric, the rule that sets distances, can evolve there with fewer interruptions. In simple terms, voids are where cosmic acceleration lives most openly. They are the laboratories in which the effect of dark energy is easiest to see. Not because dark energy is stronger there, but because there is less to hide it. This is not just a poetic statement. Models of structure formation predict that voids should expand faster than the average universe. Their interiors empty out. Their edges move outward, and galaxies near their boundaries feel a net pull toward the walls, but also an effective push away from the center as the underdense region grows. When we measure galaxy motions around voids, we can detect this differential behavior. The voids seem to be stretching more quickly, in line with the idea that where matter is scarce, dark energy defines the script. There is an everyday analogy, imperfect but suggestive. Imagine a landscape of hills and valleys under a slow, steady rainfall. In the valleys, water gathers, forming ponds and lakes. The ground is saturated, and movement is sluggish. On the slopes and ridges, the water flows more freely, responding directly to gravity, carving channels. If you want to see the pure effect of the rain and the terrain, you watch the flows on the open slopes, not the still water in the basins. In the universe, dark energy is like a very gentle, omnipresent rain of expansion. The dense structures, like lakes, are relatively insulated from its immediate flow. The voids, like open slopes, feel its influence more directly. Dark energy also changes how voids grow over time. In a universe without it, expansion would slow as matter pulls back. Voids would still exist, born from early underdensities and amplified by gravity, but their growth would be limited by the overall deceleration. In a universe with dark energy, the late-time acceleration gives voids more room to expand. Their merging accelerates. The contrast between empty regions and dense structures sharpens. The cosmic web, seen against this background, starts to look like a transient phase in a longer story driven by dark energy. In the early universe, matter dominates and structures form. In the intermediate era, which includes our present, matter and dark energy share influence. Filaments, walls, and voids all grow. In the far future, dark energy takes over, and the voids grow so large, and the distances between bound islands so vast, that the web effectively dissolves. The bridges snap. Only the knots remain. There is a quiet tension here. On the one hand, dark energy is everywhere, the same in a cluster core as in the emptiest void. On the other hand, its consequences are not felt equally. Where matter is dense and bound, local physics matters more. Where matter is thin, the global rule of expansion sets the tempo. Emptiness, once again, becomes the place where the universe's most general tendencies are laid bare. If you lean into that thought, it has a familiar resonance. In the densest periods of a human life, when obligations and relationships press close, the large-scale direction can be hard to see. Days fill with local gravity. You respond to immediate pulls and pushes. It is often only in the more spacious intervals, the stretches of solitude or reduced demand, that the underlying drift becomes visible, the way your values have shifted, the pattern of what you move toward or away from when there is no urgent force acting. Those are the personal voids, not empty in any absolute sense, but relatively free of noise, where long-term acceleration or deceleration comes into focus. Cosmology does not claim that the universe has intentions. Dark energy is not a desire, it is a parameter in the equations, measured by how supernovae dim with distance, how galaxies cluster, how the cosmic microwave background is patterned. Yet the coincidence that the most mysterious ingredient in our model expresses itself most clearly in the regions we are least equipped to inhabit invites a kind of quiet reflection. From a technical standpoint, voids are now being used as probes of dark energy. By stacking many voids together statistically, astronomers can measure how fast they grow, how their shapes are distorted by the expansion, and how light passing through them is affected. Light traveling across a void will experience a slightly different gravitational environment than light skimming a cluster. These subtle differences can, in principle, distinguish between different theories of gravity and different possible behaviors of dark energy over time. The idea is straightforward. If dark energy is truly a constant property of space, its effect on the growth of voids and the stretching of the web will follow one pattern. If it evolves, or if gravity behaves differently on the largest scales than in the solar system, the pattern will change. Voids, with their cleanliness and sensitivity, are among the best places to look for those departures. In this way, nothingness becomes a measuring stick. The regions where almost nothing has formed gain a central role in how we test our understanding of everything. It is an inversion of the usual instinct to focus only on the crowded, the luminous, the dramatic. The universe suggests, by its behavior, that to understand why it is speeding up, we must look into the places where there is least to see. There is another layer to the phrase, acceleration lives in the voids. It is not only that voids feel the influence of dark energy more purely, it is also that, as time goes on, more and more of what exists will reside effectively within such regions. As the web thins and remote clusters slip beyond each other's horizons, each bound island will be surrounded by space that, on large scales, is indistinguishable from a vast void. The typical environment of any remaining observers, far in the future, will be a small oasis in an enormous, accelerating emptiness. From their vantage point, the evidence for dark energy may be far weaker than it is for us now. Without distant galaxies to trace the expansion, without a detectable cosmic microwave background, they might infer only a static or nearly static cosmos. The very process, driven by dark energy, erases the signs of its own action. There is a quiet irony in that. The universe is most legible about its acceleration at times, like ours, when the web is still richly connected. Later, when acceleration has done most of its work, the legibility fades. It is tempting to read significance into our having appeared in this brief era of clarity. Cosmologists sometimes talk about a cosmic coincidence, that the densities of matter and dark energy are of the same order of magnitude now, even though they evolve differently over time. For most of the past, matter dominated in most of the future. Dark energy we live in the narrow crossover. That coincidence may say more about the conditions required for complex structures and observers than about any deep design. Still, it colors our perspective. We are trying to understand a process we caught in midstream, knowing that the river will eventually widen into an ocean of almost pure void. In the end, Dark energy, as presently described, is a placeholder, a way of encoding an observed acceleration in the language of general relativity, whether it truly is a cosmological constant, a quantum property of the vacuum, a slowly rolling field, or a sign that our theory of gravity needs revision, remains open. What is less open, given current evidence, is the direction of the universe's large-scale motion. It is not slowing toward a gentle standstill. It is leaning into expansion, and it is doing so most freely in the places where matter has let go. Voids, then, are not just gaps in the distribution of galaxies. They are the regions where the universe releases its attachment to structure and allows its underlying tendency to become visible. They are where acceleration lives, not because they are special, but because they are ordinary in the way the universe is most ordinary, vast, sparse, slowly deepening into a state where almost nothing interrupts the quiet drift of space-time itself. If acceleration lives most openly where there is almost nothing, the next question rises almost by itself. When we say the universe is expanding, what exactly is it expanding into? The instinctive picture is surprisingly stubborn. We imagine the universe as a kind of balloon, small at first, then swelling inside a larger emptiness. Or we see it as an explosion, matter flying outward from a point into a waiting void. In both cases, there is an inside and an outside, a thing that grows and a space around it that does not. It feels almost impossible, at first, to give up that frame. Part of this comes from how growth works in everyday life. A city spreads because there is land around it. A sound expands into a quiet room that was there already. A wave runs along the surface of water that existed before the wave. Expansion, in these situations, is always into something. There is a stage and then a movement on that stage. Cosmic expansion is not like that. In the standard picture of cosmology, the Big Bang is not an explosion that happened at some point in a larger container. It is the origin of the container itself, space, time, matter, radiation, all arise together from an initial state. Asking what the universe expands into is, from that point of view, a little like asking what the surface of a balloon expands into if the surface is all that exists. The question smuggles in an outside that is not part of the description. The balloon analogy is useful, but only if you keep its limits firmly in view. Imagine dots on the surface of a balloon as it is inflated. The dots move apart along the surface. Each dot sees the others receding. There is no special point on the surface that is the center of expansion. For creatures confined to that surface, the inside of the balloon, the air, the room, do not exist. Those are part of our embedding picture, not theirs. From their perspective, the surface simply stretches. Distances grow. There is no into to invoke. In cosmology, when we say the universe expands, we mean that something similar is happening to the distances between co-moving points in space. A co-moving point is an idealized location that moves only with the general expansion, not with local motions like galactic orbits. The rule that tells us how far apart such points are, given their coordinates, is called a metric. Over time, that metric changes. For any pair of far-separated points that are not gravitationally bound, the distance given by the metric increases. This change does not require an external space to move into. It is a change in the internal geometry, the network of distances and angles that defines space from within. Geometry here is not just lines on a page, it is the way we could, in principle, measure the size of shapes using only rulers and light signals inside the universe itself, without ever stepping outside to look at it from above. A simpler way to say this is, the universe does not need an outside to grow. It only needs a rule that lets distances between unbound regions increase over time. The observable consequences, the redshifting of light, the dilution of matter, the growth of voids follow from that internal change. Whether or not there is some higher dimensional space into which our universe is embedded is a separate question, one we do not have to answer to make sense of what we see. Still, the urge to picture an outside is strong. Partly, that is because we are creatures who always live inside something larger than ourselves. Rooms, buildings, cities, planets. We never encounter a truly self-contained space. There is always a bigger context. It feels natural to insist that the universe must also have a surrounding environment, another level into which it fits. Otherwise, where is it? But that question, for all its force, may be more about our habits than about reality. A two-dimensional being living on a curved surface can, in principle, discover that its world is curved by measuring distances and angles, without ever imagining a third dimension. The curvature is intrinsic. It can be detected from within. The extra dimension we draw when we sketch a curved surface in a notebook is a convenience for our eyes, not a necessity for the surface itself. In the same way, the large-scale properties of our universe, its expansion, its curvature, its pattern of voids and filaments can be described and measured without positing an external space. General relativity, the theory that links gravity to the geometry of spacetime, is formulated in exactly those terms. The curvature of spacetime is defined internally, by how free particles move and how light rays bend, not by how some imagined higher dimensional being would see the universe from outside. This has a quiet consequence. When we feel the need to ask what the universe expands into, we are really asking for a perspective we cannot have. We want to stand outside the whole and watch it change. We want our usual hierarchy of container and contents to extend one step further. The answer cosmology offers is not that there is certainly no outside, but that the outside, if it exists, does not play a role in the phenomena we can observe. The expansion is something space does to itself. There is a kind of existential shadow in this. We often think of our own growth in terms of moving into larger spaces, a bigger home, a wider social circle, a more expansive role. We imagine there is always an into waiting for us. But much of what actually changes over time is internal. The distances between events in our memory stretch or shrink. Things that once felt close become remote. Things that were unimaginable become part of the ordinary. The external coordinates may not shift much, but the meaning of separation and nearness does. Perhaps the more relevant question is not what we are expanding into, but how our internal geometry is being rewritten. Back at the cosmic scale, there is another common misunderstanding tied to the idea of into what. People sometimes picture the universe as a sphere in a larger void, with an edge that moves outward as expansion proceeds. Beyond the edge, they imagine, lies nothing at all. Inside, galaxies and radiation. The universe grows by eating into that nothing. The standard picture is different. There is no physical edge where the universe stops and a literal nothing begins. There is, instead, a horizon of what is observable from any given point. Light travels at a finite speed. The universe has a finite age. Put those together, and there is a maximum distance from which light has had time to reach us. That distance defines the observable universe. Beyond it, there may be more of the same, or something we cannot now predict. But the expansion does not require that there be an absolute outside, beyond which there is no space-time at all. The horizon is not a wall. It is a limit set by time and speed, not a boundary in the material. As time goes on, light from more distant regions can arrive, changing what is observable. At the same time, accelerated expansion pushes some regions effectively beyond reach forever. The shape and size of the observable patch change, but the idea of an edge you could fly to and touch remains outside what the theory describes. In that sense, asking what the universe expands into is a little like asking what lies beyond the end of time. The words can be spoken, But the concepts they string together may not match the structure of the theory that currently fits our measurements. They may be pointing to a limit of our intuition, not to a missing piece of physics. None of this forbids speculation about higher dimensions or multiverses. There are models in which our universe is a brain, a kind of sheet embedded in a larger dimensional bulk. In such pictures, one might draw a literal outside in which the brain can move. But crucially, even in those theories, the expansion we observe, the one traced by supernovae in galaxies and voids, is described by changes in the internal geometry of our brain. The embedding space is an optional story layered on top of the essentials. So, when the question arises, does the universe expand into anything? Cosmology's most careful answer is restrained. It does not say no in an absolute sense. It says that the question is not needed to account for what we see, and that insisting on an answer may be more about our discomfort with self-contained systems than about the universe itself. There is a certain relief in that restraint. It means we can focus on what is, at least in principle, knowable from within, how distances change, how voids grow, how light travels, how matter clumps and thins. The mystery does not vanish. It just shifts from a demand for an external stage to a quieter wonder at the fact that a space can rewrite its own scale without stepping anywhere else. And perhaps, in a more personal way, this reframing offers a gentler way to think about change. Not as a constant migration into pre-existing roles or territories, but as a slow adjustment of the internal distances that define our world. What is far or near, central or peripheral, important or negligible, can transform without our ever leaving the finite patch of existence we are given. The universe, on its own much larger canvas, is doing something similar. It is not filling a larger void. It is redrawing, moment by moment, what it means for anything to be far from anything else. If expansion is really a change in the distances inside space, not a motion into something outside, then the next quiet question is simple. What kind of space is doing the stretching? We grow up with one geometry, the lines in our notebooks, the corners of our rooms, the way streets cross at right angles, all teach us that the world obeys the rules of flat space. In that flat geometry, parallel lines never meet. The angles of a triangle always add up to a straight line, and the shortest path between 2 points is a straight segment that feels entirely unremarkable. It is so familiar that it becomes invisible. But geometry does not have to be flat. You can see this on the surface of a sphere. Draw a triangle on a globe, with one corner at the North Pole and the other two on the equator. Each angle can be a right angle, yet the triangle still closes. The sum of its angles is greater than a straight line. On such a curved surface, there are no truly straight lines in the sense of Euclidean geometry. There are only geodesics, the locally shortest paths that follow the surface's own curvature. There is an opposite kind of bending as well. On a saddle-shaped surface, triangles have angle sums less than a straight line. Lines that start parallel can drift apart. The whole idea of straight becomes tied to the shape of the space itself, not to some external frame. To a small creature confined to such a surface, these rules would be normal. Our flat expectations would look like a special case. When cosmologists talk about the geometry of the universe, they are asking which of these broad behaviors space follows when you look at it on the largest scales. Is it flat? Like the sheet of paper we imagine? Is it positively curved, like the surface of a sphere? Is it negatively curved, like a saddle? And does that curvature apply to space alone, or to spacetime, where time and space are woven together? In the simple cosmological models that assume the universe is the same in every direction on large scales, three main possibilities appear. A flat universe, where Euclidean geometry holds globally. A closed universe, with positive curvature. where space is finite but without a boundary, like the surface of a higher dimensional sphere, an open universe with negative curvature, where space is infinite and has a kind of built-in divergence, like a higher dimensional version of a saddle. The words open and closed can be misleading. A closed universe has no edge. You could travel in one direction long enough and eventually return to where you started, without ever hitting a wall. An open universe has no edge either. But if you travel in one direction, you never come back. Flat space can also be infinite. What distinguishes these cases is not an outer boundary, but how distances, angles, and volumes relate to one another far from any particular point. Curvature also affects how expansion behaves. In a closed universe without dark energy, gravity is strong enough, on the largest scales, to eventually halt expansion and reverse it, leading to a recollapse. In an open universe, expansion can continue forever, even without dark energy, because there is not enough matter to pull everything back. In a flat universe, the borderline case, expansion slows, but never quite stops. When dark energy is included, the picture changes. But the basic linkage between curvature and global fate remains a quiet background theme. The remarkable thing is that these differences are not just stories. They leave fingerprints on what we can observe. The cosmic microwave background, the faint afterglow of the early universe, carries a pattern of hot and cold spots with characteristic sizes. The way those spots appear on the sky depends on the geometry of space between us and the surface from which that light was last scattered. In a positively curved universe, those spots would appear larger in a negatively curved one, smaller in a flat one, just as predicted by Euclidean geometry. By measuring that pattern with growing precision, observations have found that, on the largest scales we can probe, the universe is very close to flat. Not perfectly, to infinite accuracy, but close enough that any curvature must be gentle, with a radius far larger than the part we can see. In everyday terms, our observable patch of the universe is like a tiny region on a huge sphere. The local geometry looks almost flat, even if there is some global bending we cannot yet detect. Flatness might sound boring, but it carries its own quiet weight. A nearly flat universe is balanced in a delicate way between the gravitational pull of matter and the overall rate of expansion. At least in the absence of dark energy, the fact that it appears so close to this balance has led to deep questions about initial conditions, inflation, and the mechanisms that set the early state of the cosmos. Inflation, that rapid early expansion, naturally drives curvature toward flatness, much as stretching a crumpled sheet of paper makes it look smoother. If that story is right, our nearly flat geometry is not an accident, but a memory of an early, violent smoothing. Geometry, in this sense, is not an abstract decoration. It determines how light travels, how structures grow, and how volume is distributed between voids and filaments. In a negatively curved universe, the space available at large distances grows faster with radius than in a flat one, giving even more room for emptiness to dominate. In a positively curved universe, volume grows more slowly. The interplay between curvature and expansion feeds into how quickly voids can form and how thoroughly they can come to rule the available space. There is also a subtler point. The kind of curvature that matters here is intrinsic curvature. The curvature you can detect from within by making measurements with rulers, clocks, and light beams. You do not need an outside perspective. On a curved surface, a two-dimensional being could discover that the angles of large triangles do not add up as expected. In our universe, we play the same game with distant galaxies and relic light. We listen to how space responds to its own contents. That reliance on internal measurement has an echo in our own lives. We often imagine that to know who we are, or where we stand, we would need some external vantage point, an impartial outside observer. But most of what we can actually know comes from within the fabric of our own experience. The angles between choices, the distances between who we are and who we thought we were. The way paths that seemed parallel slowly converge or diverge over time. The curvature of a life, if there is such a thing, is also intrinsic. It is written into the relationships between its events, not in some imagined view from above. Returning to cosmology, the near flatness of the universe does not mean it is simple. Local regions can have strong curvature where mass is concentrated. A black hole is an extreme example, a region where space-time is so warped that not even light can escape. Galaxies, clusters, and filaments all bend the paths of light and matter in their vicinity. On those scales, the geometry is messy and particular. It is only when you average over enormous distances, spanning many such structures, that the smooth, nearly flat background emerges. Voids, again, play a special role. Being underdense, they contribute less local curvature. Light passing through them travels slightly different paths than light weaving through clusters. By carefully mapping these effects, astronomers can refine their measurements of large-scale geometry. The emptier the region, the closer its behavior comes to that of the ideal background space described by the simplest cosmological models. In that way, voids are like open windows onto the geometry of the universe itself. Flat, open, closed. These words, on their own, do not settle the emotional meaning of a universe. A closed universe might seem comforting, finite and self-contained. An open one might seem more lonely, stretching without bound. A flat one might feel precariously balanced. But those reactions are ours, not the universe's. Geometry does not carry intention. It is a set of quiet rules governing how distances and angles relate, how paths bend, how volumes grow. Still, knowing that our cosmos is, as far as we can tell, remarkably close to flat changes the background feeling of the story. We do not live on the surface of a small, tightly curved sphere, doomed to recollapse in some near epoch, nor do we inhabit a wildly open saddle that flings things apart without resistance. We live in a space that, on the largest scales, behaves very much like the flat geometry we learned in school, but infused with an expansion that rewrites distances over time and with voids that hollow out most of the available volume. Against that background, the question of what expansion really is becomes even more geometric. If curvature can be defined and measured purely from within, then so can change in scale. The universe does not expand into anything. Its geometry evolves. The fabric that decides how far apart things are and how those distances change is its own reference. And this brings us, quietly, to another step. If curvature and expansion are intrinsic properties of space-time, then perhaps the same is true of whatever we call expansion in our own narratives. Not movement into new territories, but adjustments in the distances we live with every day, to others, to our past, to our imagined futures. Cosmology cannot answer those personal questions. It can only offer, as a distant mirror, a picture of a space that needs no outside room to grow, and of a geometry that, once accepted, reshapes how we think about what it means for anything to move apart or come together at all. If space can carry its own curvature without leaning on anything outside it, then the thought is hard to avoid. Perhaps its expansion is not an extra motion laid on top, but something written into what space and time are. In everyday life, we treat space and time as separate. Space is where things are. Time is when they happen. General relativity ties them together into space-time, a single four-dimensional fabric of events. A point in space-time is not just a location, but a location at a moment. A world line is the path an object traces through this fabric, joining all of its moments into a continuous thread. In that picture, Gravity is not a force pulling on objects from a distance. It is the bending of spacetime itself. Objects in freefall simply follow the straightest possible paths, called geodesics, through a curved geometry. Near a massive body, these paths curve toward it. We interpret that as gravitational attraction. No external force is needed. The fabric itself dictates how things move. Expansion enters as another feature of this geometry. Instead of imagining galaxies flying apart through a neutral stage, general relativity allows solutions in which the distances between widely separated geodesics increase with time. Even when each geodesic, locally, is just minding its own business, the straightest possible paths can still diverge if the fabric between them is stretching. Mathematically, cosmologists describe this with something called a scale factor, a function that tells how the typical distance between co-moving points changes with cosmic time. A co-moving point is an idealized location that participates in the overall expansion but has no extra local motion. If the scale factor grows, the distance between two such points grows. Expansion, then, is nothing more and nothing less than the statement that this scale factor increases. It is a property of spacetime itself, encoded in the metric that defines distances. Not an additional velocity laid on top. This sounds abstract, but its consequences are very concrete. When light travels across an expanding universe, its wavelength is stretched along with the fabric of space. The redshift of distant galaxies, the way their light is shifted toward longer wavelength, is a record of how much the scale factor has changed between emission and detection. We do not see galaxies racing through a pre-existing void. We see the history of the metric imprinted in the light that reaches us. The distinction between motion through space and expansion of space becomes especially clear when you think about bound systems. A galaxy, a solar system, a planet, even your own body, are held together by forces much stronger than the gentle stretching of the cosmic background. Within those regions, the metric is effectively different. Local curvature created by mass and energy dominates over the global trend. The atoms in a measuring rod do not slowly drift apart because the electromagnetic forces binding them are far stronger than cosmological expansion on that scale. So expansion is not an instruction that every distance must grow. It is a rule about how the geometry behaves when you look far enough out. Beyond the reach of local binding, it is an intrinsic behavior of spacetime in the large. You could, in principle, detect it from within by mapping many geodesics, comparing the separations between distant galaxies, reading the redshift pattern of light, and never once invoking an external room into which anything moves. The fact that expansion is intrinsic also means that asking for a center or an edge is usually a category mistake. In the standard cosmological models, the universe looks the same in every direction from any typical point. Once you average over large enough scales, every observer sees other distant galaxies receding, with a recession speed proportional to their distance. There is no special location singled out as the place from which everything expands. The change is global and relational, not local and directional. This has a quiet parallel in personal experience. When your inner world changes, there is often a temptation to locate that change at a single point, a decision, an event, a revelation. But much of what matters happens in the slow alteration of the distances between things inside you. How far a memory sits from your present concerns. How close a possibility feels. How much space a loss occupies. There may be no single center or edge to that process. The geometry of meaning shifts, and the shift is real, even if no external coordinates move. Intrinsic expansion also reframes how we think about time. In these cosmological models, time is not a uniform parameter ticking independently of everything else. The rate at which the scale factor grows depends on the contents of the universe: matter, radiation, dark energy. Those contents, in turn, evolve as expansion proceeds. Time and expansion are entangled. The history of space-time is not just a sequence of instants laid side by side, but a sequence in which the very notion of distance changes. Voids illustrate this especially clearly. In the relatively empty regions between filaments, the geometry is close to the simple expanding solutions of general relativity. The local metric there is dominated by the large-scale behavior of space-time, with very little interference from clumps of matter. Galaxies skirting the edges of voids follow geodesics that are shaped more by the global expansion and less by local gravitational wells. When we measure their motions, we are more directly sampling the intrinsic expansion than when we study galaxies buried deep in clusters. In that sense, voids are not only spatial emptiness but conceptual clarity. They show expansion as it appears when other complications fall away. They are places where space-time does what it does with less negotiation. The stretching of distances is not blocked by strong local curvature. The geometry speaks in a simpler accent. The idea that expansion is intrinsic also affects how we think about alternative theories. If someone proposes that the redshifts of galaxies are caused by some process other than expanding space-time, say, by light losing energy as it travels through a static medium, the proposal has to reproduce not just one observation, but the whole suite of phenomena that follow from a changing metric, the detailed pattern of the cosmic microwave background, the growth of large-scale structure, the way voids and clusters evolve, the time delays in gravitational lensing. So far, the picture in which expansion is a built-in property of space-time weaves those pieces together with a coherence the alternatives have struggled to match. Yet even this coherence does not close the story. General relativity tells us how space-time curves and stretches in response to energy and momentum, but it does not explain why there is space-time at all, or why it carries the particular form of dark energy we infer. Expansion as an intrinsic property is, in that sense, like a rule in a game whose board we did not choose. We can learn the rule, test it, use it to predict what happens next, and still not know why this rule rather than another holds. There is a kind of humility built into that position. We inhabit a patch of space-time whose geometry is doing something specific, expanding, accelerating, hollowing out voids, thinning filaments. We can measure and model these behaviors from within, using the paths of light and the motions of galaxies as our rulers. We can describe expansion without any need for an outside five, but the fact that the rule is internal does not mean it is self-explained. For our purposes, though, one conclusion is enough. Expansion is not a layer draped over space. It is part of what space and time are, at least in the regime we can observe. To ask where it happens most honestly, we do not need to look for a frontier where the universe meets some external nothing. We need to look into the places where the metric is least disturbed, where space-time is allowed to express its large-scale tendencies with the least resistance, which brings us back, almost inevitably, to the largest and quietest of those places, the great underdense regions, the supervoids and anomalies that seem to test the limits of our standard picture. If expansion is written into space-time itself, and emptiness is where that writing is easiest to read, then the most extreme voids become not just curiosities, but test lines, where the script of the universe may show its small hesitations, its marginal corrections, and perhaps its deepest commitments. If expansion is part of what space-time is, and voids are where that behavior shows itself most clearly, then it is natural to ask what happens in the rare places where emptiness itself seems to go to extremes. Most voids are already enormous by any human standard, but some structures stand out even against that background. Astronomers sometimes call them supervoids. A supervoid is not just an underdense region, it is an underdensity that stretches across hundreds of millions of light-years. A basin that gathers and merges smaller voids into a single, sprawling absence. The word is informal, but the intuition behind it is simple. These are the places where nothingness has grown particularly bold. You might imagine that emptiness is simple, but supervoids arrive in the data as puzzles. When light from the early universe, the faint microwave glow that fills all of space, passes through a large underdense region, the changing gravitational landscape can leave tiny fingerprints on that light. Photons climbing out of slightly shallower wells in an expanding universe can lose a little more energy than they gained when they fell in. The result is a patch of sky that appears just a bit colder than average. This effect has a technical name, but the idea is straightforward. The evolving structure of the universe can subtly cool or warm the fossil light that reaches us. In some directions, the microwave sky shows patterns that may hint at the presence of unusually large or deep voids along our line of sight. In particular, there are regions that look colder and more coherent than simple statistical models would suggest. Efforts to link these patches to supervoids in the foreground have produced a mix of promising hints and stubborn uncertainties. The data are noisy, the structures messy, and the sky gives us only one realization to study. Even so, the possibility that the largest holes in the matter distribution leave marks on the oldest light we can see has become one of the more intriguing ways in which absence announces itself. Anomalies like these force cosmology to do something it does not always enjoy: question its own assumptions about typicality. Much of the standard picture assumes that, on large enough scales, the universe is statistically uniform and isotropic, meaning it looks the same in every direction and from every typical point. Once you average over many structures, anomalies are places where that statistical serenity seems to falter. A supervoid apparently larger or emptier than models predict. A cold patch on the sky more pronounced than expected. A structure that stretches coherence across distances that should, in principle, be too large to share a common origin. There are two broad ways such anomalies can be read. One is as chance. In a universe that is vast and noisy, rare fluctuations do occur. Given enough volume and enough possible patterns, some region will always look stranger than the others, simply by accident. The other reading is as a hint that the underlying model is incomplete, that the rules we are using to generate our expectations need refinement, or that some additional ingredient is at work. Cosmology, being cautious, leans first toward chance. It asks whether our sense of strangeness is sharpened by hindsight, whether we would have found the same region remarkable if we had defined our measures differently in advance. It checks for observational biases, for quirks in instruments or data analysis that might mimic anomalies. Only when such checks are exhausted do people seriously entertain the idea that a given feature might be a signpost toward new physics. Supervoids occupy an awkward middle ground in this process. On the one hand, large voids are expected. The growth and merger of underdense regions over cosmic time naturally produces a spectrum of sizes, including some that are much larger than the typical void. On the other hand, particular claimed structures have, at times, seemed to strain the standard narrative, hinting at correlations or sizes that sit near the margins of what the models comfortably allow. The community's response has been a mixture of skepticism, interest, and repeated attempts to improve both simulations and observations. What matters, for our purposes, is not the outcome of each specific debate, but what all of them share. They all treat emptiness not as a background, but as a subject. They measure the properties of the largest regions where almost nothing has formed and ask whether those properties fit within the rules we thought we understood. The anomalies, whether real or illusory, are tests of how seriously we are willing to take absence as a source of information. There is a quieter parallel in personal life. Often, it is the stark or unusual emptiness that forces us to re-examine our own model of how things are supposed to go. A long silence where there used to be frequent contact. A stretch of time in which none of the usual markers of progress appear. An emotional flatness where we expected intensity. We can treat those intervals as mere bad luck, noise in the pattern. Or we can let them pose a harder question. Was our picture of how life would unfold ever accurate? Or did we quietly assume a level of structure and fullness that was never guaranteed? Supervoids play that role for cosmology. They ask whether our expectations about typical structure, about how uniform the universe is allowed to be, are as solid as we think. They are the extreme cases that probe the edges of our theories. Even when they ultimately fall within the allowed range, they force us to confront the fact that most of space is more like them than like us. The phrase, final meaning of dominance, sounds heavier than the data alone can carry. But it points to something simple. Voids dominate in several overlapping senses. They dominate volume. If you choose a point at random in space, you almost certainly land in a region of very low density. They dominate future structure. As expansion accelerates, they grow and merge, thinning the cosmic web and isolating bound islands of matter. They increasingly dominate what can be known. Over long enough times, most of the universe will slip beyond any given observer's horizon, leaving each island surrounded by a practical void. There is also a more subtle dominance. By focusing our attention, voids force a change in perspective. They undermine the intuition that matter, by virtue of being tangible and luminous, is the primary architect of reality. Instead, they suggest that the large-scale behavior of the universe is structured more by where matter is not than by where it is. The expansion field, the geometry, the influence of dark energy, all express themselves most plainly in the places least encumbered by mass. In that sense, nothingness is not a passive remainder. It is an active participant in the cosmos, not because it exerts a force of its own, but because it offers the least resistance to the intrinsic tendencies of spacetime. Where there is less to hold back, the underlying rules play out more fully. The dominance of voids is the dominance of an environment in which the universe can most easily do what it does anyway. If you carry that idea one step further, the existential echo almost writes itself. Much of what shapes a life is not only the events and objects that fill it, but the spaces between them, the unscheduled hours, the unchosen paths, the silences where no message arrives. Those voids are not just deficits. They are the conditions under which certain possibilities can emerge and others fade. They reveal, sometimes more clearly than the crowded days, what the underlying tendencies have been all along. Cosmology, of course, cannot tell you how to live. What it can do is offer a mirror on scale. It can show you a universe in which luminous structures are fragile threads in a vast, deepening darkness, and yet real, active, and capable of contemplating that darkness from within. It can show you that dominance, at least here, does not mean that the thing in control is loudest or brightest. It may simply be what occupies most of the room in which everything else tries to move. So when you look up at a clear night sky, most of what you see is not the stars, but the darkness between them. Behind that darkness, further still, lie distances so large that the word between starts to lose its meaning. Almost all of the universe is like that, silent, thin, stretching. Our cluster, our galaxy, our small world, exist on the edge of one of many basins of nearly nothing. What you do with that knowledge is, in the end, yours. You can treat it as a piece of trivia, as a kind of distant weather report about a scale you will never touch. Or you can let it sit a little closer the next time you step outside at night or fall quiet in a room that has just emptied. You can allow, for a moment, the thought that you are already living inside a universe whose main feature is absence. And that meaning, if it is to exist at all, will have to be made here, in one of the thin, bright threads. If you want to keep walking through questions like this, You do not need new instructions. You can simply stay with the unease a little longer. Return to these ideas when the sky is dark again. Or press play the next time you feel the pull of that almost nothing that surrounds everything you know.